Welcome to the natural log function differentiation. In this video, we will recall what natural log means, as well as learn a new definition of it in a calculus way. We'll explore its graph, some properties, and then finally go over the derivative rules for natural log and some examples. At the end, we will also revisit how to find relative extrema, and in this case, for a function involving natural log. This right here is the definition of the natural log function, and this is a very calculus way to write this definition. We'll explore this more in the next video. Let's instead take a look at what natural log means in a more exponential way. As you hopefully recall from pre-calculus, natural log is a function where the base is e, and so we have a secret silent little e down here to represent the base. Now e is a transcendental number. It is important in a lot of higher level mathematics, especially calculus, and it's approximately 2.718. It is irrational, and so it goes on forever. Right now, you should locate the button on your calculator for e. Now, looking back at this function, y equals the natural log of x, let's rewrite this a little bit to see what this really means. We can think about this as being the base e to the y value equaling our output of x. This is simply going from logarithmic form to exponential form. If we create an xy table, we can figure out a couple of the coordinate points on our function y equals the natural log of x. I'm actually going to plug in some y values because that would be a little bit easier. Let's plug in the y value of 0. If we plug in a y value of 0, we'll have e to the 0, and anything to the 0 power equals 1. And remember, e does not have to be intimidating. It's simply 2.718 ... So that is how we get one of our main coordinate points on this function here, 1, 0. Let's plug in another simple number for y. Let's raise e to the first. So if we plug in 1, e to the first is simply itself, which would be e. The reason I plugged in these two coordinate points is mainly because they were simple, but these are kind of the main 2 points on our graph y equals the natural log of x. Now, if you take a look, if we plug in any negative number, let's say we plug in -1, e to any negative number will always output a positive. E to the -1 means 1 over e. E to the -2 means 1 over e squared, simply just using the property of a negative exponent. Mainly, if we plug in any negative number, my point is that we'll always get a positive output. So this output here would just be 1 over e. And I'm saying output, but it's really the x value. Next, what if we plug in a very large value? Let's say we plug in a value of 10. Well, if we plug in a value of 10 here, we'll have e to the 10th as our output. Now, the main 2 values that are important here are right here. This is telling us that we know we have the coordinate points 1, 0 and e, 1 on the graph of y equals the natural log of x. Now, what else does this tell us? If we take a look at our original function, y equals the natural log of x, that means that when our x value is 1, our output 0, so the natural log of 1 is 0. It also means that if we input e, the natural log of e is simply 1. So we know these important facts, which we'll explore later in the video as well. We know that the natural log of 1 is 0, and we also know that the natural log of e is 1. Let's take a look at all of this on the graph. We can see here from graphing y equals the natural log of x on Desmos that it's sort of an arc, and it becomes less and less steep as we go on to the right as x approaches infinity. We can also see that we cannot have any negative x values here or 0. We do have to plug in a positive number for x, and that is because of what we saw before, that no matter what we plugged in for e to the y equals x, we always got a positive x out. So we can only plug in positive numbers. We do see that the coordinate point 1, 0 is on our graph here. That is our x-intercept. The next important point that I wanted to plug in was the number e, and so I'm actually going to go to the ABC here and actually click e. We can see that e is approximately 2.718 here. It's in between 2 and 3, and our output is 1. So these are 2 important values on the graph of y equals the natural log of x. Then as we zoom in and out here, we can see that this is actually what the graph of the natural log of x looks like. Here we will talk about some of the properties of our natural log function. The domain, as we saw from our graph, is all positive real numbers, and the range is all real numbers. We saw that just from our graph and from our brief discussion about what the natural log function means. Second, the natural log function is continuous, meaning there's no gaps or holes or vertical asymptotes. It is increasing, and it's also one-to-one. Recall that one-to-one means that its inverse is also a function. Now, it's continuous, and we saw that from our graph, but it is also increasing. We can prove that a function is increasing, if you recall, by proving that its derivative is always positive for the domain. So we are actually going to learn real quick, before we officially write it down, the derivative of the natural log. Our function is the natural log function, and its first derivative is actually 1 over x. So the derivative of natural log of x is 1 over x. We want to prove that it's increasing by showing that this first derivative is always positive for all x values in our domain. Well, since our domain is all positive x values, that means 1 divided by any positive number is always positive. Therefore, we can conclude that since f prime of x is always positive, especially for all x in the domain, we can come to the conclusion that f of x is increasing. We also saw that the function literally was increasing as we look from left to right. We saw that the y values were constantly increasing. So we proved it using calculus, and also we saw it on our graph. Then, for number 3, the last property is that the graph is concave downward. So the graph of the natural log of x is concave down. So in a similar way that we prove that our graph is always increasing, or the function's always increasing, we can prove that the graph is always concave down by taking a look at its second derivative. So once again, our function is the natural log of x, and we already found that its first derivative is 1 over x, or we can write as x to the negative 1. I write it that way so we can easily find the second derivative, which would be using the power rule for differentiation, negative 1 over x squared. Now, if we take a look at our second derivative and we plug in any x value in our domain, so any positive number, if we plug in any positive number for x, this x squared is always positive, and then negative 1 over that positive number will always be negative. So we come to the conclusion that our second derivative is actually always negative, again, for all x in our domain, which I can write as all x in our domain. Therefore, our function, f of x equals the natural log of x, is concave down, since the second derivative is negative. Let's now take a look at some log properties. These are properties that hold true for the log log with base 10, as well as the natural log ln base e. These are some, especially numbers 1, 2, 3, and 4, that you have learned previously in pre-calculus, but it's always good to get a refresher. Let's skip number 1 for now. The natural log of a product, we can actually break apart into the natural log of the first factor plus the natural log of the second factor. This works for an infinite amount of factors being multiplied. The natural log of a to the n, if we have an exponent here, we can actually bring it out front, so it becomes n times ln of a. And in a similar way to number 2, number 4 is the natural log of a quotient, which can actually be broken apart into the natural log of the numerator minus the natural log of the denominator. Now looking at number 1, this is something we already talked about previously in this video. The natural log of 1 is 0, and I actually want to write a property 1.5 here, that the natural log of e is 1. So be sure to include this last property here. I'll call it property 1.5. The natural log of e is 1. So these are 2 important natural log values to know. Let's briefly use these properties to expand some natural log expressions. In this first one, we have the natural log of 9/10, so we're going to use property number 4 to break this apart into the natural log of 9 minus the natural log of 10, and that is it. In number 2, I'm actually going to rewrite this. This is really the natural log of 3x plus 2, and since it was a square root, it's raised to the 1/2. Using property 3, we can bring that exponent out front, So it's 1/2 the natural log of 3x plus 2. These are just some quick practice for using those properties of logs because we will see how to use them in a more calculus way when taking the derivative of certain more challenging natural log functions. Here is the heart of the video, the derivative of the natural log function. We have already sort of learned this previously in this video. We saw that the derivative, d dx, of the natural log of x is simply 1 over x. Now x does have to be greater than 0 because that is the domain of our natural log function. Now what if we have something that's a little bit more complicated than just x inside our natural log function, say u, some other function? The derivative of the natural log of anything, the natural log of u, is, using the chain rule, 1 over u times the derivative of u with respect to x. That can be simplified as writing u prime over u, since this is u prime and it's being multiplied by 1 over u. So, in a simpler way, the derivative of any natural log function is the derivative of the inside of the function over the original inside of the function, u prime over u. Let's take a look at 3 examples for finding the derivative of different natural log functions. Up top here in pink, I wrote our rule for the derivative of the natural log of any u. In number 1, our u value is 3x. So I know that my denominator is going to be 3x. The numerator is going to be the derivative of that. So I'll write this one out in depth. Our u value will be 3x, and our u prime is 3. Because of the power rule. So the derivative here is going to be 3 over 3x, which simplifies to 1 over x. In number 2, we're taking the derivative of the natural log of 3x squared. So I'll do this one without writing it all out. We're going to take, in the denominator, the original inside of our natural log function. And then in the numerator, we are going to have the derivative of that inside. So the derivative of 3x squared using the power rule is 6x. Simplifying, 6 over 3 can cancel to 2 over 1, or just 2, and one of the x values can cancel top to bottom. So we'll be left with 2 over x. In number 3, we're taking the derivative of a product, x times ln x. That means we're going to have to use our product rule. So we'll call x times ln x here our product. And remember, the rule for product rule is u times v prime plus v times u prime. Now do not get this confused with the u that is part of the natural log rule. This is simply just another way to write two factors here being multiplied and their derivatives. So I'm going to take the first, our u value here is x, and our v value here is ln x. So first we're going to have x, then we need to multiply by the derivative of the natural log of x. The derivative of the natural log of x is 1 over x, plus our second term, v, the natural log of x, times u prime here. The derivative of x is just 1. Simplifying, x times 1 over x is 1. ln x times 1 is ln x. So our final answer here is 1 plus ln x, using the product rule, and the derivative of the natural log of x equals 1 over x. These next 3 examples are doing the same thing. We're finding the derivative of natural log functions. These ones are a bit more challenging. If we take a look at number 4, we're taking the derivative of the natural log of x squared plus 1. So in the denominator, we're going to write originally what's inside our natural log function. Then in the numerator, we have the derivative of what's inside. Again, this is all using the chain rule. So it's 1 over x squared plus 1 times the derivative of the inside. The derivative of the inside is 2x. We cannot simplify this x over x here. That is because x squared is part of a greater factor, x squared plus 1. So you cannot cancel anything here, and this is our final answer. In number 5, we are finding the derivative of the natural log of x all raised to the 4th. Now, what we can do here, Well, the first thing we have to realize is that it's not the natural log of x to the fourth. It's the natural log of x raised to the fourth. Therefore, we are going to be using the power rule. The power rule states that we bring the 4 out front, leave what's on the inside alone, and raise it to 1 less. Then, using the chain rule, we multiply by the derivative of the inside function. The derivative of the natural log of x is 1 over x. So we can write this in a simpler way. Out front, we can have 4 over x, then the natural log of x, the entire thing raised to the third. Again, it's not just x raised to the third, it's the natural log of x, the entire function, cubed. In number 6, we have the natural log of a square root. Earlier in this video, we talked about the properties of logarithms, including natural logarithms. So I'm going to actually rewrite this, and we'll be taking the derivative of the natural log of x plus 1 raised to the 1/2. Now this is the inside part being raised to the 1/2. That means that we can use our property of logs and bring this 1/2 out in front of the natural log. So we're really taking the derivative of 1/2 times the natural log of x plus 1. Taking the derivative, the 1/2 stays there. And then taking the derivative of the natural log of x plus 1, we use our natural log derivative rule, which says it's a fraction, and the denominator is what's inside the natural log, and the numerator is its derivative. The derivative of x plus 1 is 1. Simplifying this, we will have 1 over 2 times x plus 1. What about natural log functions that have an absolute value? Well, it's the same idea. If we have the derivative of the natural log of the absolute value of u, we again are still doing the same thing. U prime divided by u. So the derivative of what's on the inside divided by the original what was on the inside of the natural log function. In this case here, our u value, in this example, our u value is the cosine of x, and therefore our u prime would be negative the sine of x. So let's write that out. We have that our u value here is the cosine of x, and then our u prime is negative the sine of x. So finding f prime, using our rule for the derivative of natural log of an absolute value, we'll have u prime over u, which in this case is negative sine of x over cosine of x. Using our knowledge of trigonometry, sine over cosine is tangent, therefore f prime is the negative tangent of x. In our final example here, we're going to use one of the applications of differentiation, finding relative extrema of a function. So the first thing that we need to do to find relative extrema is look at the derivative, so find the derivative. So we will be finding dy dx, so the derivative of y with respect to x, we took the derivative of y. On this side, we're going to take the derivative of the natural log of this quadratic trinomial. So we're going to use our derivative rule for natural log that we've been using. So what's on the inside of our natural log, that u value is in the denominator, and in the numerator is u prime, so the derivative of this guy in here. The derivative of each term will be 2x plus 2. So our numerator is 2x plus 2. Again, we cannot cancel anything here, but the next thing we need to do in order to find the relative extrema is we need to figure out when our derivative is either 0 or undefined. Because our derivative is a fraction, finding where it's 0 means setting the numerator to 0, and finding where it's undefined means setting the denominator equal to 0. So setting our numerator to 0 will actually give us x equals negative 1. Setting our derivative to undefined means setting the denominator to 0. Again, this is how to find our critical points. We find where our derivative is 0 or undefined. So because it's a fraction, we'll set the denominator to 0 to find where it's undefined. Taking a look at this, my first thought is, can it be factored? The numbers look almost too good to be true, but there are not two numbers that multiply to 3 that add to 2. If those were swapped, it would be better. So in this case, I'm going to actually use the quadratic formula and see if we actually have any solutions. So because our quadratic formula involves a square root, I'm going to take a look at the discriminant. The discriminant is what's under the square root, b squared minus 4ac. So I'm going to see if that value is positive or negative. If it's negative, we're not going to have any solution. So b squared minus 4ac. So we'll have b squared minus 4ac. This is a negative number. We'll have 4 minus 12, which is negative. So therefore, we have no solution to this. So that means our only critical point is x equals -1, because this never equals 0. Now I do want to make sure, because this is a natural log function, I want to make sure that what's on the inside here is positive. That's the domain of any natural log function. As we know, its input has to be positive. If we plug in -1 for x here, we'll have 1 minus 2 plus 3. That is a positive number. So let's take a look at our critical point, x equals -1. If we plug in -1 for x, we'll have 1 minus 2, so -1 plus 3. So if the natural log of 3 is our output, so our coordinate point is -1 natural log of 2. I want to know if this value is either a relative minimum or a relative maximum. I could use either the first or second derivative test. I'm opting to use the first derivative test because the second derivative kind of looks like a pain to find. So I'm going to use the first derivative test. So I'll write y prime up here, which is dy dx, and here's our x value. We do want to test to the left and to the right of -1. So we know already that when we plug in -1 to our first derivative, we get 0. We already determined that. It's a critical point. Next, I need to test to the left of -1. What is the number to the left of -1? I'll plug in -2. Let's make sure that -2 works and keeps this positive here, i.e. is it in our domain? So if we plugged in -2, we'd have 4 minus 4 plus 3. We still have a positive number inside our natural log function, so that means -2 is a part of our domain. So if we plug in -2 to our first derivative, we'll have a negative number up top, and we'll have a positive number down below. So a negative divided by a positive is a negative. Then if we plug in a number to the right of -1, i.e. 0, that is still an okay number to plug in. If we plugged in 0 to our derivative, we'll have a positive number up top and a positive number down below, making our first derivative positive. So because our first derivative goes from negative to positive, that means our original function decreased, then increased, making x equals -1 where a relative minimum occurs. So our function looks something like that. That means that the coordinate point -1 ln2 is a relative minimum. Taking a look at the graph of this function here, we do see that we have a relative minimum at x equals -1, and its output, this is the natural log of 2, is 0.6931. So that is the relative minimum of our graph of our natural log function. After watching this video, you should feel a little bit more comfortable with properties of logs, get a good refresher, and we learned the derivative of the natural log function. We kind of delve back into derivatives a little bit because next we will talk all about integrating the natural log function. Stay tuned.